Okay, so the title of the presentation here is The Geothermal Paradox, How the Earth's Second Largest Heat Source May Be Driving the Most Recent Warming. This has been one of the criticisms of this, and we'll address this later on, that, well, it's such a small amount of energy relative to, for example, the total amount of solar energy that we get, that this can't be driving any climate change whatsoever. So, as we said, until recently, there has been very little attention paid to the impact of geothermal heating on global temperatures. Again, the argument being that, well, there's really not enough heat here to make a difference. And in fact, this has been one of the final conclusions of the latest IPCC report, which is not worth the paper that it's printed on, as far as I'm concerned. It's a political statement. It's not a scientific statement. The vast majority of the Earth's geothermal heat is emitted by volcanoes and hydrothermal vents in the middle of the world's oceans. This is from Davies and Davies, and the areas here in pink and in red are the high geothermal flux areas. These are what are called the spreading zones. This is where plates are coming apart in the Earth's crust. And we have, for example, here we have the Mid-Atlantic Ridge, which goes from the Arctic all the way down to the Antarctic. We have the East Pacific Rise over here off the coast of South America. And these spreading zones are very well known. They're very well mapped. And we actually don't have a lot of data as to how much geothermal heat is coming out of it. These are estimates. And every time I read a new study on this, the estimates keep getting higher and higher. But we do have a proxy indicator. So here's this mid-ocean ridge system. We've got the East Pacific Rise here, the Mid-Atlantic Ridge. Can you see my cursor there? I'm just curious. Can you see the cursor?
I muted the microphone so that we wouldn't have interference. Yeah, we can see your cursor very clearly.
Well, great. That's great. So I will be pointing to things. So here we see the Mid-Atlantic Ridge and the Southeast Indian Ridge, Central Indian Ridge. These are very, very well known. And again, these are this is called the Mid-Ocean Ridge system. And it's really a system, a 60,000 kilometer long system of volcanic mountains and associated what are called hydrothermal vents. And these hydrothermal vent fields are really the key to the flow of the geothermal energy. Here we can see a map of this on sonar and LiDAR. We see that this again is very well mapped. This is old knowledge. These things have been known about for a very, very long time. And if we take a close-up view of this, if we take a look at these areas where the plates are coming apart, these mid-ocean ridges, we see that they're technically referred to as rift zones. That is, one plate is pulling apart and this is coming in this direction, the other plate is moving in this direction, and underneath it is a chamber of magma, that is heated rock that has been melted. And as these plates move apart, as they drift apart, this magma is able to seep up to the surface, and it's able to vent itself in these rift zones. So these volcanoes, which tend to be large explosive events, but more quietly, these hydrothermal plumes come up from these vents that are called black smokers and white smokers. We'll show you how this looks in just a second. This is where most of the heat comes up, and here we're going to focus in on this magma chamber here. We see this is what we're looking at. That is, the heat from the mantle moves up. It's extremely hot, 1200 degrees C. And then we see through this vast system of fissures and outcrops, this is where we get the heat being released into the overlying oceans. The black smokers, they say here, 80 to 200 degrees C. Some of them can get up as high as 400 degrees C. That's the extreme edge. And meanwhile, the temperature at the bottom of the ocean is about 4 degrees C. So we have as many as 30,000 of these vent fields on the planet. They estimate there may be as many as one vent field every 2 kilometers throughout this entire system. 30,000 is a large number of vent fields. Now, the paradox here is that on average, the global geothermal flux is low. It's about 1/10 of a watt per square meter, but that's a global average. And we do know that the heat from the mantle performs a tremendous amount of work. Most notably, it's able to move the Pacific plate 4 inches per year. That's the lithosphere and the water sitting on top of it. And it widens the Atlantic basin by about 1 inch per year. It can also eject, all that heat can eject enough ash to cool the globe by many degrees. We saw this at Krakatoa and Tambora, for example. And it can eject ash and water 35 miles into the atmosphere, which is what happened in the 2022 Tonga eruption. Now, move some things around here. These mid-ocean spreading zones are the proxy indicator that we're going to use. Oops, sorry. These are what we're going to use as our, just trying to get this down the bottom. There we go. These mid-ocean spreading zones, another name for the mid-ocean ridges, is a good proxy indicator of how many seismic events that we have. That is, the number of seismic events is a proxy indicator of how much geothermal heat we have. And here is a study done in the that was presented in the journal Nature that says seafloor hydrothermal systems are known to respond to seismic and magmatic activity along these mid-ocean ridges, often resulting in locally positive changes in hydrothermal discharge rate, temperature, and microbial activity, and shifts in composition occurring at the time of earthquake swarms. Corresponding regional effects have also been observed. So the relationship is actually quite simple. The correlation I've seen on this is 0.97. It's extremely high. The more seismic activity you have in these mid-ocean zones, these mid-ocean spreading zones, the more heat is being released, the more heat flux you get out of these areas. The thermally driven convection of seawater occurs through the oceanic crust on all ages at the seafloor spreading axis, on mid-ocean ridge flanks, and in the ocean basins. Most of that hydrothermal heat loss occurs on the mid-ocean ridge flanks, where the temperatures are lower than the seawater flux corresponding. Seawater flux is correspondingly larger. The estimated heat loss on the flanks is so large that upwelling must occur over a large fraction of the seafloor, less than 65 million years old, and that's the majority of the seafloor. So we know that there's a large area involved in hydrothermal flux. And what this says is that this is a very active system over a large part of the ocean, and the more seismic activity we have, the more heat we can assume is occurring out of these areas. So, if you will, the number of earthquakes is what we call a proxy indicator. It's the same as tree rings, or what are called varves, layers in lakes, or ice core rings, or oxygen isotopes. It gives us an indication as to how much geothermal heat is coming up. So the more seismic activity, the more geothermal heat is coming up. So to get back to my student's original question, well, I mean, I'm jumping ahead of myself here. Where this is a game changer is that it's in the ability to impact what is known as the thermohaline circulation. The thermohaline circulation is a gigantic conveyor belt of ocean water that moves around the globe. One circuit of this takes about 1,000 years. And the game changer here is that the oceans contain 1,000 times as much heat as the atmosphere. And what this does, more geothermal heat, as opposed to directly heating the atmosphere, it enables geothermal heating to enhance the ocean's ability to transfer heat. In other words, the more heating we have at the bottom, the more intense this thermohaline circulation moves. It's a rather simple relationship, and we're going to look at some of the studies that actually point to this. It's well documented in the scientific literature. So here's a three-dimensional view of this thermohaline circulation. It goes by many names. It's also called the meridional overturning circulation, the overturning circulation. That is, it refers to the fact that temperature and salinity drive density differences in the oceans, And those density differences cause it to upwell and downwell. So here we see some upwelling in the Pacific Ocean and downwelling up here in the North Atlantic Ocean, and circulate again in this huge three-dimensional pattern. And we're going to cite a few studies here. This one is by Ballarata in a journal called the Climatic Past Discussions. It says, although the ocean is largely heated and thermally driven at the surface, several recent studies suggest that the OGH, ocean geothermal heating, can also affect the ocean dynamic and heat budget. By applying spatially constant or variable heat flux in the ocean general circulation models, forced with the present day climate, it is shown that the OGH is a significant forcing that can weaken the stability of the water column, warm the bottom water, and strengthen the thermal haline circulation. And that's a critical point. Okay, this system, this giant conveyor belt, is heated at the bottom, and the more heat you apply to it, the more intense or the faster this thermal haline circulation operates. Another study in geophysical research letter says that the additional destabilizing geothermal heat flux tends to promote a more vigorous full depth overturning, having approximately 10% greater volume flux than with no bottom heating. So they estimate that just at base geothermal levels, the system operates at a 10% heightened intensity as if there were no bottom heating whatsoever. Another study that came out in geophysical research letters by Adcroft and Scott says that geothermal heating induces a substantial change in the deep circulation, which is larger than previously assumed. The numerical ocean model responds most strongly in the Indo-Pacific, with an increase in what's called the meridional overturning, that is the rate at which the oceans overturn vertically, of 1.8. SV stands for sphere droops, and a sphere droop is a metric that is used in water transport. A sphere droop is equivalent to 1 million cubic meters of water per second. The entire output of the Earth's rivers is about 1.5 sphere droops. So geothermal heating is significant. So this enhances the existing overturning by approximately 25%. So obviously geothermal, these ocean studies have shown that the geothermal component is significant. Here, another study in the Journal of Geophysical Research Letters shows that the geothermal heat strongly intensifies meridional overturning circulations. The Atlantic cell in the globally heated experiment of Adcroft is weaker than ours. What they did is they turned up the amount of geothermal flux. They said, let's increase the amount of geothermal energy into the system. And their heat flux was twice as large. That is, they were saying, assuming we crank it up by a factor of 2, we found a huge difference in the magnitude of the overturning circulation. So that we know that when you vary the amount of geothermal heat flux, it does have a huge impact on the rate at which the overturning circulation moves. Here's another Geophysical Research Letters article that says that they're finding that in the Atlantic, we're finding things are progressively strengthening by 5 to 10% in response to the deep density changes in the South Atlantic. So we know that there's a connection between geothermal activity in the South Atlantic and throughout the entire Atlantic basin. So we know here that the Atlantic part of this, the Atlantic segment of this, called the Atlantic meridional overturning circulation, has been increasing in response to deep density changes. Now, here's where the rubber meets the road. We can calculate the number of seismic events that we have at these mid-ocean ridge spreading zones. I call them MOSA. It's mid-ocean spreading zone seismic activity. And we were able to plot this back to 1977, and it's culled from what's known as the GCMT catalog, which is a complete catalog of seismic events 5.3 and greater. And we come up with a rather interesting distribution. We see that, now people say, well, it's such a small number. Well, this is this is actually an exponential, technically a logarithmic relationship. In other words, if you have, say, 100 earthquakes up here, let's say for argument's sake, 100 earthquakes, 5.3 to 6.3, then that means you have 1,000 earthquakes, 4.3 to 5.3. 10,000 earthquakes from 3.3 to 4.3. 100,000 earthquakes down to 2.3, and 1 million earthquakes down to 1.3. So we're talking hundreds of thousands of earthquakes totaling up in the millions. Difference between our low point here in 1977, where it was approximately 20, which is approximately 200,000 undersea earthquakes in these mid-ocean spreading zones, all the way up here over 100 by a factor of 5. We also see another interesting thing in this curve. We see that there have been distinct jumps in the curve. And the most outstanding one we see, where we see an actual doubling within a 3-year period, is from 1995 to 1998. It goes from 30 to 60. And this is a remarkable jump, and it has stayed elevated since 1998. But 1995 is what I call, this is where it turns up, an inflection point in the system. And this inflection point is very, very important because we see a lot of things that happen after 1995. Here we can see the global temperatures as detected by satellites. These are the most accurate. They have the widest spatial coverage, and I think this is the gold standard in measuring atmospheric temperature. This is put out by the University of Alabama at Huntsville. Roy Spencer and John Christie put this product out. And we say, okay, let's put the two curves together. And if you put them together, they match up, except you get a case of double vision. That is, you see that there's an offset. And we find that the offset, if we wash this mathematically, we find that the offset's about 2 years. In other words, there's a 2-year lag from the time you get an increase in seismic activity till the time you see an increase in global temperatures. This lag effect is very pronounced and it's very clear. So if we put the two curves together with this 2-year lag effect, this is what we get. That is a very, very tight fit. For such a noisy system as global temperatures and mid-ocean earthquakes, there's a lot of noise going on in here. We've got changes in cloud cover, changes in snow and ice coverage. We've got changes, variable solar output. We have gravitational changes going on here. So this goes back to the temperature curve starts in 1979, and the mid-ocean seismic activity curve starts in 1977, and it comes out here to 2022. We see that the curves fit beautifully with a very high correlation of 0.74. Now, I hear this all the time, and I'll address this a little bit later on. All the time, well, correlation isn't causation, and that's exactly the argument that the tobacco companies used, against the medical profession. I found a very high correlation between smoking and lung disease. So we know that this correlation is strong, and there has to be something behind it, and we have to sort of figure out what's going on here. If we look at the global temperature changes since 1978, we see that by far the largest change occurs at the North Polar region. Then we have the Northern Hemisphere extratropics, which is from 30 to 60 degrees, 20 to 60 degrees north latitude. The tropics, which is from 20 degrees south to 20 degrees north. Then the Southern Hemisphere extratropics, which is from 20 degrees south to 60 degrees south, and then finally the South Pole. We have this huge increase in temperature at the North Pole and virtually no temperature increase at the pole. And everything in between is neatly stepped down. We have this progressive temperature change that grades nicely from the North Pole all the way down to the South Pole. Now, if carbon dioxide was driving this system, we would expect to see a much more even distribution of temperature change. Because carbon dioxide, they do measure carbon dioxide at the South Pole, and they're virtually identical to the carbon dioxide readings that they have in Hawaii, which is, just north of the equator. So we see again that it has a north to south gradient, a very distinct gradient and a very sharp gradient. And what my research has shown when you do a deep dive in the literature, we're looking at two major what are called heat sinks in the global system. That is the Western Pacific out here, and in the North Atlantic and the Arctic are two areas where we see significant change, and the significant change is driven by blockages to the thermohaline flow. The system is impeded here in Australia and in Southeast Asia. That is, this warm surface flow actually runs into Australia along with Indonesia, Malaysia, and is slowed down. And we see by the time it gets to the North Atlantic, it pools up in the Arctic. So the Arctic, if you will, is sort of a cul-de-sac for the thermohaline circulation. So we have a major roadblock here, and we have a cul-de-sac up here. And we're going to address those 2 points now. Next 12 slides will provide concrete evidence that starting in 1995, the intensified thermohaline circulation significantly impacted temperatures along with a host of other geophysical phenomena in the North Atlantic and the Arctic. So let's first look at this Atlantic sector here. And we see an index known as the AMO, the Atlantic Multi-Decadal Oscillator. This was actually discovered by Professor Mann. And it shows that in 1995, the AMO index flipped from a cool phase to a warm phase. Distinct jump. So 1995 is when it first turned positive. There was a slight negative reading in 96, but it's been positive ever since then. So 95 is our inflection point, which again perfectly corresponds with the inflection point that we saw in the seismic activity. Here we see what we consider to be an average temperature field for the North Atlantic and for the Arctic, and you can see that the North Atlantic has been greatly warmed up, as has the Arctic. You've got some blue areas here along the coast. This is due to freshwater runoff from the continents, but the Arctic basin has also warmed significantly. So when you have a positive AMO, this is the temperature that you want, that you expect to see. And so, for example, what's happened is that you'll notice it starts here in the southern hemisphere. The thermohaline circulation flows northward. It becomes intensified in the subtropics, and what we now have is an intensified and faster flow from the subtropics into the northern hemisphere. So what you're doing is you're transporting large amounts of heat from this region here up into the North Atlantic. This was a landmark study that was done just a few years ago by Oziel in Nature Communications, and they found that there was a rapid intensification of the North Atlantic currents in 1996. And they state that the Arctic marine biome, shrinking with increasing temperature and receding sea ice cover, is tightly connected to lower latitudes through the North Atlantic. By flowing northward through the European Arctic corridor, the North Atlantic waters transport most of the ocean heat, but also nutrients and planktonic organisms toward the Arctic oceans. Using satellite-derived altimetry observations, we reveal an increase up to twofold in North Atlantic current surface velocities over the last 24 years, starting in 1996. So this pattern started to become prevalent in 1996 and continues to this day up to the present. We also see a tremendous increase in hurricane activity starting in exactly 1995. Okay, this is the, I'm trying to move this out of the way. I have this bar up here at the top. Can't read the top part. But anyway, we have the warm phase of the AMO going back to the late 1970s, then the cool phase throughout the 1980s and into the early part of the 90s, and then this warm phase where the hurricanes become much more active starting exactly in 1995. We also see that the ice mass in Greenland started to decline from its peak in 1995. Global cloud, I'm sorry, this is cloud cover. I apologize, this is cloud cover. We say the same thing globally. In 1995, we started to see a decline in global cloud cover. As you warm the atmosphere, it can hold more water vapor. And as it holds more water vapor, you have less cloud cover. And this is what's really going on here. So, and this becomes a feedback, that is less cloud cover allows more sunlight in, so it reinforces what we're seeing. We see that the freeze dates in the Hudson Bay region have changed dramatically, starting again in 1995. We see what's called the subtropical gyre. So a sudden start, then this curve goes back to 1960. We see here's 1990, here's 2000, 1995. We see a huge jump up in the sea surface temperatures south of Greenland and Iceland. And here's what that subpolar gyre looks like. The subpolar gyre here saw an increase in temperatures starting in exactly 1995. We also saw changes in Arctic temperatures north of 80 degrees latitude. That is the spring and the fall temperatures started to increase dramatically in 1995. That's again is our inflection point. This data goes all the way back to the late 50s. We see it's fairly constant. And then starting in 1995, we see this jump up here. We see the same thing for the winter temperatures. They're a little bit lagged. They start warming up around 2000. Summer temperatures in the Arctic are not impacted. But fall, spring, and winter all started around 1995 or shortly thereafter, started to increase. The Northern Hemisphere sea ice also started to decline in 1995. This comes from the National Snow and Ice Data Center at the University of Colorado. We see here that it had plateaued in the 80s, and then in 1995 it takes a dip down, comes up a little bit, and then has been down, trending downwards ever since. So that explains things in the Atlantic Basin. If we are to look here at the Pacific sector, enhanced thermohaline flow will also cause more warm water to accumulate in the Western Pacific. The physiography and the bathymetry are such that this region restricts the flow of what is known as the equatorial current, and that creates a vast reservoir of warm water, which is the driving force behind El Nino events. Here we see the north equatorial currents coming in this direction, moving westward across the Pacific. Here we see it at the eastern sector. Here we see the western sector. That is, we have what we call the Western Pacific warm pool that represents a store of heat that can and that heat can get redistributed across the entire Pacific Basin. And when the pressure and wind field conditions switch from a neutral phase, this is when we get into an El Nino phase. So what happens here is that the equatorial currents push water from the eastern Pacific into the western Pacific, and here it literally gets blocked by Australia, Indonesia, and Malaysia. The flow is highly constricted, and as a result, warm water can start to accumulate in this part of the Pacific, and it's called the Western Pacific Warm Pool. And here we see a study that was done by Kidwell back in 2017. It shows that in 1993, here we see that Western Pacific warm pool. It's relatively cool. This is total heat content in gigajoules, I believe, is the unit of measurement here. By the time we get to 2014, that warm pool, as we can see here, is much larger and it's much warmer. We can also see that what's called the thermocline depth has also changed abruptly in 1995. The thermocline depth, and the thermocline is the transition zone between warm water sitting at the very surface and much colder water sitting down beneath it. It's very, very distinctly marked in the tropics. You have a pool of very warm water sitting at the top, much, much colder water sitting beneath that. And we can see that the thermocline depth this goes back from 1982 to 2022. This is in months. Actually, from pre-1995 was at an average depth of 155 meters below the surface. The thermocline then jumped up to 165 meters. That is, that Western Pacific warm pool, in addition to getting bigger and warmer, also got deeper. And here we see what happens when that Western Pacific warm pool actually dissipates. That is, the wind field switches. As to why it switches, they don't know. But what happens is that you are, through constant frictional force with the winds, you are constantly piling up this water here in the Western Pacific, and eventually those winds start to relax, and that warm pool starts to slosh back in an event known as an El Nino, which is what we're experiencing right now. We've had 3 of these La Nina events, which are normal events, but now we're getting an El Nino where the water is sloshing back across all the way down the coast of South America and up the coast of North America. So the warmer temperatures have been spread out from this Western Pacific warm pool all the way out to the Eastern Pacific. It goes from the international dateline all the way to the Americas. We see that the currents of the Pacific are also impacted by this. That is, the Kuroshio current and the Kuroshio extension are also strengthened by this increasing thermohaline flow. Here we see the Kuroshio current, which comes off the Philippines current, and it washes the southern shore of Japan and then goes out into the Pacific Basin. And this Kuroshio current and the Kuroshio extension have become more intense, and they've become warmer since around 1995. And here's a study done by Lamb. It says, warm stems from the surface waters that collect in the Western Pacific Ocean along the equator, called the Western Pacific Warm Pool. The Kuroshio current takes these waters north past the Japanese coast and then upwards, eastward at latitude 36 northward, joins the open Pacific. At this point, it becomes the Kuroshio current extension. Today, these currents are warming 2 to 3 times faster than other areas of the ocean. Ocean model studies and observational data also show that the Kuroshio current expansion is shifting northward and increasing in its transport capacity. Now I say, okay, well, this is really nice. Can we actually see this in the global temperature distribution? And yes, here's a map of sea surface temperatures. That was from April, 2 months ago. Here we see this extreme warming of the Kuroshio current and the Kuroshio extension. That is, the northern tier of the Pacific Ocean is experiencing much warmer temperatures. And here we see the effects of the El Nino, that on the south shore, that on the western shores of South America. And here we see the effects of the warmed Kuroshio and Kuroshio extension. So the sea surface temperatures are clearly being impacted by the dissipation of this warm pool. We also see higher temperatures up here in the Arctic again. So, in summary, we should direct our research away from this, which shows the carbon dioxide curve and the temperature curve, and we can see that there's a huge divergence between these curves over time. That's because these carbon dioxide models grossly overestimate the amount of warming that we're having. And we should be directing our attention towards this hypothesis, and here's the model that I've developed in the form of a flow chart, and this hopefully ties it all together. We see that greater mid-ocean geothermal heat flux, which is driven by increased mid-ocean seismic activity, which we've documented, intensifies the thermohaline circulation. In the Pacific sector, that increases oceanic heat transport into the Western Pacific. That amplifies our El Ninos and the Kuroshio warms, which gives us increased tropical and extratropical Pacific temperatures. In the Atlantic sector, I lost something here. Sorry. In the Atlantic sector, the increased oceanic heat transport into the North Atlantic gives us less ice and cloud cover, which lowers the albedo or the reflectivity of the Arctic, and that helps to increase North Atlantic and Arctic temperatures, but we also get direct heating from more warm water coming in here. And this is an interesting feedback loop that we now have. And that's why the Arctic has probably warmed the greatest of all the Earth's regions since the 70s. So now critics have tried to attack this on two basic points. First, the first argument is that there's not enough heat escaping from to the surface to directly warm the overlying atmosphere to an appreciable degree. And second, the high correlation between mid-ocean seismic activity and global temperatures does not signify causality, as spurious results can arise if confounding variables are omitted from the experimental design. And this one makes me crazy. This point number 2 just drives me up a wall. We can easily refute these arguments in the following way. First, and we will stipulate the first point, although there is not enough heat, there we go. Although there's not enough heat to directly warm the atmosphere, we have modeling evidence showing that oceanic geothermal heat intensifies the thermohaline circulation. That intensified flow acts as a heat pump to distribute an increased amount of oceanic heat into two major heat sinks, the North Atlantic Arctic, and it's called the Arctic amplification, and the Western Pacific, i.e. the Western Pacific warm pool. We also have irrefutable empirical evidence to corroborate the modeling results. So when you have modeling evidence that's supported by empirical evidence, then you know you have something of value. And a third point that we can use as a point of refutation is that the entire chain of environmental changes, i.e. higher global temperatures, reduced cloud cover, amplified El Niños, etc., is anteceded by the change in mid-ocean seismic activity. Okay, that is, the mid-ocean seismic activity occurred in 1995, and all these other changes occurred shortly thereafter. We call this in statistics, this is referred to as Granger causality. And it strongly infers that a cause, i.e. one change occurs first, in this case it's the seismic activity, drives time-dependent effects, i.e. other perturbations occur afterward. So the seismic activity in the mid-oceans increased first, and then we see all the changes to global temperatures, snow cover, ice cover, El Nino amplifications, thermocline depths in the Western Pacific. Those all followed after the 1995 uptick in seismic activity. And ultimately, understanding the climate is a classic epistemological problem. We all know the metaphor of a bunch of people only seeing one small part of the elephant, and they describe it in many different ways. You know, it's a spear, it's a fan, it's a wall. The modern thinking today, people like Greta Thunberg and Al Gore is, oh, it's carbon dioxide. But actually, this is a very, very complex system where we have drifting continents, we have changes in solar activity, we have changes in subaerial volcanic activity, changes in submarine volcanic activity, changes to the thermohaline circulation, and changes in Earth's orbit, gravitational forces also. And this is what they're ignoring. They've pretty much thrown all this out and said, we can only blame it on carbon dioxide. And carbon dioxide, the anthropogenic loading of carbon dioxide to the atmosphere of all the greenhouse gases, by my estimates, at the highest estimate, is 1% of the total greenhouse gas load to the atmosphere. It's probably less. So I refer to Alfred Wegener, one of the great heroes of the geosciences. He says, scientists still do not appear to understand sufficiently that all Earth sciences must contribute evidence towards unveiling the state of our planet. It is only by combing the information furnished by all the Earth sciences that we can hope to determine truth here. And this is exactly the tenet that is being ignored to this day. You know, they're saying it's CO2 and everything else is irrelevant. And actually, as far as I'm concerned, CO2 is highly irrelevant and everything else has to be considered. So, as a postscript, I love this one here on the left. It says, of course all scientists agree when you censor the ones who don't. And this has clearly happened. And finally, trust the science is the most anti-science statement ever. Questioning science is how we do science. And the entire scientific process is being abridged, and it's being violated by not allowing dissenting voices on this. As you said, it's the empty chair discussion. They refuse to show up. They cancel us. They won't publish our work, and they don't want to discuss it. So I thank you very, very much for your indulgence.